So we continue the lesson by groups of permutation. Okay, some of these theorems are simple. I mean, I want to convince you they are correct by giving some examples. And then, of course, examples are not proofs in mathematics, I know that, but probably you will understand that this method will actually can be rigorous as well. So let us say that I have a phi binary bijective. So phi, for example, belongs to S5. Okay, and I write phi, for example, in cyclic notation to be 1, and then 2, and then 4. Okay, so you know that this belongs to a group. Yes, the group of S5. And what was the binary operation for this group? It was the composition of functions. Yes. Okay. Now, if I ask you what is the order of phi, so order of phi, there is some interference here. Yes. Yes. So order of phi is equal to, say, I want to know what is the order of this phi. My claim is that the order of this phi, the order of any cycle, is actually equal to the length of the cycle. Okay, so in this case, I want to convince you that phi to power 3 is the identity. So, and I told you, remember, I reserved this letter for the identity bijective. Okay, so why is that true? First of all, you see that you don't see 3 here, you don't see 5 here. So it means that if I ask you what is phi of 3, do you remember what is that? 3. Phi is left constant with this, so it is 3. So this means definitely phi to power 3 acting on 3 is again what? Because if I apply phi 1 more, this becomes phi squared, this becomes phi of 3. So let me do it step by step one time. So if I apply phi 1 more time, this becomes phi squared. And then this becomes phi of 3. But what is phi of 3? Phi of 3 is 3. So this means that phi squared of 3 is also 3. And for the same reason, you immediately understand that phi to the power of 3 acting on 3 is again phi acting on 3, which gives me 3. Yes? So this means that it is very clear that phi to the power of 3 leaves 3 intact. Do you agree what happens for this one? Can you see that? If I apply this on 5, what do you think will happen? When I send 5 in, this will not touch 5 because 5 does not appear here. So for the same reason, phi to the power of 3 of 5 is also 5. Is that right? Okay, but now what do you think will happen for phi? If I have 1, I apply phi on it, what does it give me? Phi acting on 1 gives me 2. And if I apply phi on it 1 more, it gives me 4. So you see, I want the identity element. So I want to see how many times I have to apply phi so that every element goes back to itself. So if I apply phi 1 more, what will happen? 4 goes to 1. So this means that if I apply phi 3 times on 3, I get 3. 3 times on 5, I get 5. 3 times on 1, I get 1 again. And if I do it less, I will not reach to 1. So it means that on the one hand, hopefully it would be clear for you, phi to the power of 3 will leave every element intact. But if I have a less power than 3, you see 1 is not going back to 1. So this means that it is not possible to find a smaller number for which phi to that power becomes identity. Is that clear? Any questions? Yes?
Why do you take phi of 3? Because 3 isn't in the permutation.
No. My claim is to show that first of all, it is in the permutation, it is not in the cyclic notation because I am working in S5. So in principle, this phi is a shorthand notation. Do you remember for what? For this matrix notation that I have 1, 2, 3, 4, and 5. And then here, phi of 1 is 2, phi of 2 is 4, 3 is left intact, 4 goes back to 1 and 5 is left intact. Yes? Now my claim is that I want to show that phi goes to 3 is just epsilon, is the identity. If I want to prove this claim, I want to show that I have to show that phi 3 acting on all these 5 elements gives me the same number back. Yes? This tells me that phi to power 3 is the identity, but it doesn't guarantee yet that the order is 3. I was trying to convince you that if I apply it less number of times, at least 1 will not go back to 1 itself. So this means that is not identity. Is that clear? Okay, so remember this. In the homework that you are doing, you can refer to the theorems and you can use them. You don't need to prove them, okay? So from now on, remember, the order of any cycle is very simple. Count the number in it, and that's the order. Is that right? Okay. Let us go to the next one. And this one, I want you to know, I will not prove it rigorously, but I hope that you feel that this should be correct, okay? So if I give you, this is a very important theorem and result, the order of a permutation of a finite set written as a product of disjoint, you see I have colored the disjoint, cycle is the least common multiple of the lengths of the cycles. Yes, okay? So what do I mean by that? So I mean that, for example, let us work with 5 again, and let me write alpha as a product of 2, for example, disjoint cycles. So 1, 2. So let me work with S7 this time. Alpha is 1, 2, 3, and then I have 4 and 5. Okay. So this alpha belongs to S7. I know how alpha acts on 1, 2, 3, 4, and 5, but there is no information written here about alpha acting on 6 and alpha acting on 7. If you remember, there was a convention. So if that is not the case, it means that they are left intact. So this means alpha takes 6 to 6, 7 to 7, but 1 to 2, 2 to 3, 3 to 1, 4 to 5, 5 to 4. That's the meaning of alpha. Yes? Okay, now the question is that if this was not there, and if I ask you what is the order of this one only, that is this theorem, you immediately say 3. If that was not there, the order is 2. But now I have a product of 2 cycles, but the cycles are disjoint. If they are not disjoint, and if you want to use this theorem, first you have to write it as a product of disjoint cycles, and then use the theorem. And the theorem is extremely simple. So what is the order of this one alone? 3. What is the order of this one alone? 2. So you take the least common multiple. It means the order of alpha becomes the least common multiple of what? Of these 2 numbers, 3 and 2. Least common multiple means the smallest number, so that that number is divisible by 3 and 2 simultaneously. So what is that? 6. So the order of this one is 6. Okay, I want you to think that one part of it is very simple. I can immediately convince you that alpha to power 6 is the identity. This is the simple part. The next part, that is the smallest one, that's also not hard, but you have to sit down and do it yourself. It's not very hard. If you don't know how to do it, then we can discuss it. Why do you think alpha to power 6 is epsilon here? So let us calculate. Alpha to power 6 is equal to 1, 2, 3, 4, 5, totally to power 6. Can I write 6 here and there individually? And if yes, why? Because I hope that you know that in algebra, if you have AB in a group to power n, there is no guarantee that this becomes A, N, B, N. In general, this is not correct, unless you know something more. Yes? Not abelian is the best one, but even if A and B, just A and B commute, that is enough. When you say abelian, it means all the pairs commute. Yes, you are right. But if A and B commute, yes, I can write this one to power n is equal to A to power n, B to power n. Okay, now my question for you, I just want you to remember, refresh your memory. I am claiming that for this case, I can do that. Can you tell me why? we had a theorem just the very last minute of the last time. So what was the theorem? Can you mention it?
Disjoint cycles always commute.
Commute. So that is why it is important that for using this theorem, the cycles are disjoint. This and that are disjoint cycles. It means that they don't have any element in common. So this means that there was a theorem so that I can commute them. So it means that they commute, and whenever they commute, I can use this formula. Yes? And then what do I do now? I can write it as 1, 2, 3 to power 3 to power 2. And the next one I can write it 4 and 5 to power 2 to power 3. Yes? But then what is this one? This is a cycle of length 3. I am raising it to power 3, which is exactly the order. So this becomes epsilon. So this becomes epsilon to power 2. This is a cycle of order 2. I am raising it to power 2. So that is also epsilon. Epsilon means the identity, but I have a power of 3. And this becomes epsilon to power 5, but which is epsilon, because epsilon is the identity. Okay, but for example, what you have to convince yourself of is that when I raise it to power 5, 4, I will not get epsilon. This I want you to think about it in a way that you can generalize it. Of course, in this case, it is very simple. Raise it to power 5 and you see it doesn't work. But you need to discover the pattern so that you can generalize this theorem for any case. Is that right? So, okay. For example, if we want to use this theorem to solve this problem, order of permutations, determine the order of the following permutation. Okay, so let me write it here for you on the board. So alpha is equal to 1, 2, 3, up to 8. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then I have 4, 9, 7, 5, 6, 8, 2, 1, and 3. Am I right? Okay, so the question is that what is order of alpha? Yes? Okay, so do you have any suggestions for me? Yes?
If we create these cycles, well, one of length 5.
Yeah, we write it as a product of disjoint cycles, which was a very standard exercise in this context and we practiced. Exactly. So this is the permutation I have. So I will start from here. So what was the method? Do you remember? You start from the smallest number, which is not mapped to itself. So here is 1. Yes. And then I see that 1 goes to 4. So I would write 1 goes to 4. And then I ask myself 4 goes to 5. So 4 goes to 5. 5 goes to 6, and 6 goes to 8. And you know that you always have to return. Do you remember? And you return always to the first number because that's bijective. So and as you see, this happens. So I close my cycle here. And then I start with the smallest number, which is not in my list, and it is not mapped into itself. So what is that number? 2. So I start with 2. 2 goes to 9. 9 goes to 3. 3 goes to 7. Yes. 7 goes to 2. Return. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have used all of it. Yes. So and now this alpha is the same alpha, but the good thing is that I have written it as a product of disjoint cycles. So if I ask you what is the order of alpha, this becomes LCM, least common multiple of this number 1, 2, 3, 4, 5, and 4, which is which number?
20.
20 is the smallest number, which is simultaneously divisible by 5 and 4. Okay? And this is the homework problem. So I chose to put this as a homework problem. So, yeah, you know what to do immediately now. Yes? Okay. So definition, this is also important. It's a very simple definition. Transposition, or sometimes as you see they are called 2 cycle. A transposition is a cycle of length 2. That's called a transposition or a 2 cycle. Yes? If I have a cycle of length 2, we call it transposition or simply 2 cycle. Okay. So this is a very, very important theorem. So every permutation in Sn is a product of transpositions. So it means that it doesn't matter what you choose, what alpha I choose, for example, I can always write it as a product of transpositions. And one thing I want you to remember, this is not uniquely determined. You can write one single permutation in a very different way, in different ways as a product of transpositions. But something will be left invariant, and that is the number of transpositions involved. Okay, so first of all, let us try to understand this a little bit. It's not a very hard theorem at all. So, but there are 2 formulas. I have written it in a separate slide. I want you to remember that. So, let me test your intuition first. If I write a cycle here, 1, 2, 3, 4, let us pretend that I am working in S sub 4. Okay, so this alpha, let us work in S4, for example. Now I want to test your intuition. Can you come up with an idea? I want you to write this, decompose it as a product of transpositions, not necessarily disjoint. That might not be even possible. So I want you to tell me, how can I write this alpha as a cycle as a product of transpositions? Yes.
So maybe just like 1 goes on 2 in one parenthesis, and then the second one with 2 goes on 3.
Yeah, very good. So that intuition works. Yes. So what I can write, but we have to prove it a little bit rigorously. Okay. So what I want to say is that let me write another one beta here, and I want to follow you. So 1 goes to 2, and then you said 2 goes to 3, and then you said 3 goes to 4. Okay. Okay, so how can you prove to me that alpha and beta are the same? And I want you to somehow memorize this way of decomposition. Yes? So, we want to prove that alpha and beta are indeed the same. Yes? How should I do that in technically speaking, yes?
That was not my question.
I have.
Don't we need 4 goes to 1?
No, you will see no. Okay, yeah. So how should I prove alpha is equal to beta? Alpha is a function, beta is a function. I want to prove that alpha and beta are the same. Equality of 2 functions means equality of domains. I don't have any problems there because the domain of both of them is numbers from 1 up to 4. So I have to show that alpha acting on any element from 1 to 2 to 4 is the same as beta acting on the same number. Yes?
A, B, C, D, alpha, and beta.
I'm just talking it for these numbers, but you are right, and technically speaking, we can do that. So what I'm saying is that, tell me, so if alpha acts on 1, so if I have 1, and I ask you alpha act on 1 gives me what? Look here, alpha is here. Alpha act on 1 gives me 2. Okay? But now tell me, 1, I send 1 to beta, what do I get? 2. So I want to send 1 here. This will, even though it doesn't see 1 because there is nothing here. So 1 passes here. It doesn't see 1. 1 passes here, and 1 goes to 2. Yes? So this means that alpha goes to 2 again. So for 1, it works. Yes? But for the other ones, let us check this for immediately. So what happens for 2? 2 under alpha goes to where? 2 goes to 3. And now I want you to tell me 2 goes to what number under beta? So I want send 2 in. This doesn't see 2. 2 send it to 3. And this will, it doesn't change anything because 3 is not here. So 2 goes to 3. Yes? So that's also correct. So they are acting the same so far. Yes? If I want to ask you what about 3, so I will send 3 to alpha. It gives me 4. And now I will send 3 to a beta. What is the answer? If I send 3 here, 4 goes out because 3 turns into 4 and 4 goes out. This does not change 4. This does not change 4. So 4 goes out eventually. That's also working. And then for 4, I send 4 to alpha. So it gives me what? 4 goes to 1. But if I send 4 to beta, I hope that I get 1. Yes? When I send 4 here, 4 is changed to 3. 3 goes out. 3 goes to 2. 2 goes out. And 2 goes to 1 eventually. Yes? So this is more or less the proof. So if you don't believe in it, write it with letters and then test the idea again. Okay, so because I don't want to spend that much time because there are much more important things that are not very intuitively clear. Is that right? This one, I would say it is more or less intuitive, but there is also another way which is not that intuitive, and I always forget it myself. So there is another standard way. Might be, of course, you can find other ways as well, but the other one is a little bit strange. These things I remember them, but if there are other methods, I don't know. We have to sit down and look. So this is why you start with 1 and with the last one. Be careful, you start from 1 and last one on the left, and then 1 and this one again, and 1, this one again. So it means all of them are involved with the first element. This is not that obvious, but let us try to test it, and then you can sit down and work it out that this works for all the cases as well. But let us test this. We already know what alpha does, sends 1 to 2 and etc. But let me call this one this time gamma, and I want to ask you, what do you think will happen if I send 1 to gamma? So what will happen? If I send 1 to gamma, 1 goes to 2, none of them will change 2, so I receive 2. So far so good, because alpha will also take 1 to 2. But now if I ask you, what happens if I send 2 to gamma? So what happens? If I send 2 to gamma, the first one will change 2 to 1, 1 goes out, 1 goes to 3, 3 goes out, and this will not change 3. So 2 goes to 3. Yes, is that right? Yes. Alpha also sends 2 to 3. And then you can do the other one. So for example, if I say 3, I send it to gamma, what will happen? This will not change. This will change 3 to 1. 1 goes out, and then 1 goes to 4. So 3 goes to 4. Yes, 3 goes to 4 by alpha as well. And then finally 4, it goes to 1, hopefully. Let us check. So if I send 4 here, this will not see 4, this will not see 4, this will send 4 to 1. That's correct. Okay, so there is nothing deep in this theorem. If, of course, this is not a proof, but you can write a cycle with letters A1, B1, A1, A2 up to AM, and try to convince yourself that this is always working. That's not very hard. Okay, but do you think now that the theorem is proven? What was my goal? My goal was to show that if you give me any permutation, I can write it as a product of only transpositions. Yes? You agree that this is done now? Why? Because here, what we learned before, we learned that we can always write any given permutation as a product of disjoint cycles. Yes? Now what we learned is that any given cycle can be written as a product of transpositions. So I write a product of transpositions for this one, I write a product for transpositions of this one, then I look the whole entirety, it will be a product of transpositions. And this is not claimed that the transpositions are disjoint. So weird. Is that right? Okay. And the intuitive way of understanding, for example, if I give you random numbers from 1 to 5, for example, let me write them randomly. 3, 5, 2, 1, and 4. Yes? Intuitively, it means that you can put them in order just by transposition. Transposition means what? It means that it leaves everything intact, but it will interchange only 2 of them at a time. Yes? So is that understandable? For example, I interchange these two, one will sit here. I interchange these two, one will sit here. It's a very non-optimized way, of course. And then I do another interchange, one comes here. So, and then hopefully you see that I can, by using transpositions, I can put them in order, 1, 2, 3, 4. Yes? Just by doing transpositions. More or less, that is the meaning of this theorem. Any questions?
Maybe stupid question, but why does not 1 gamma go to 4?
What? 1 gamma? Here.
Yeah, why does it?
So I send 1 to here. Yes?
So it's always from the.
Always from right, because that's the composition. So that is when I write alpha beta, I mean alpha O beta. Alpha after beta. Yes. Because this is very old fashioned. Because of this, many algebra books write functions like this, 4f. This is very confusing, so they have changed the idea. So if you open an old algebra book, because of this confusion, they write the argument of the function on the left, so that this becomes the first one. But in calculus and everywhere, we do it from right. When I write f O g, I read it f after g. So g is the first one I see. So this is why I'm not sending from left, I'm always sending from right. Did I answer your question? Okay. So now let us go to this one. And I have written different ways. You see, 1, 2, 3 is a cycle of length 3, but in S5. You should be able to immediately convince yourself that all of these decompositions are correct. So this 1, 1, 3, 1, 2 is exactly this weird decomposition I told you. The next one is the one she told us, the more intuitive way. But I try to find other ways as well. So you can go and sit down and convince yourself that all of them are equal to the same cycle. And you see that there is no uniqueness at all. Yes? But one thing becomes very clear. How many cycles, how many transpositions are involved in the first line? 2, remember. How many in the second one? Again, 2 transpositions. How many in the third line? 4. And how many in the last line? 6. So what is left the same is the number, is the parity. Parity means what in mathematics? Parity means evenness or oddness. So the parity of the number of transpositions involved for this decomposition is always the same. So if you manage to write it as the product of even number transpositions, everyone should come up probably with a different answer, but the number of transpositions should be even. And if you come up with a cycle that can be written as an odd number of transpositions, then it is always odd. Is that clear? Okay, but this is not trivial at all. Okay, so that is the and these are the formulas that I actually explained on the board. I want you to somehow remember it, especially for the exam. It might be good. Oh, so I have to fix this. I don't know what has happened. I hope that there are many of them are like this, but I will fix them for you. But let us. I think it is readable, or is it? No, it is not very good readable. You have to read the second row first. If a permutation in Sn can be written as a product of R transpositions as well as S transpositions, then R and S have the same parity. Okay, so I will write it here for you, but then when I want to upload it, I will fix it. It's already there, but there is a bug in my code. I don't know what happens when I render it. This happens. Okay. So, what does it mean? It means that if, for example, let us say that we are working in Sn, and you give me one element from the group Sn. So let me call it alpha. So, for example, I managed to decompose alpha to a number of transpositions. For example, let me write tau for transposition 1, tau 2, and then up to tau n. Okay. So let me be careful. So let me use another letter, M here. Okay. So you give me alpha, something like this, and I use what I know. According to this theorem, it is guaranteed that I can write alpha as a product of transpositions. These are transpositions. It means they are cycles of length 2. Okay? And then I give alpha to another one of you, and you sit down and manage to decompose it to a product of transpositions. But your transpositions may be different from my transpositions. So you might say that I get tau prime 1, tau prime 2, and up to tau prime k. So I was able to write alpha as a product of m transpositions, but when I pass alpha to you, you sit down and think and manage to write it as a product of k transpositions. My claim is this: m and k always have the same parity. What does it mean? It means they are simultaneously even or they are simultaneously odd. If I don't do any mistake and I manage to write my alpha as a product of even number of transpositions, if I pass alpha to you, you might not come up with my decomposition, you might come with a different one, but the number of transpositions will still be even. And if I do it in odd number of ways, you have to also find it in odd number of ways. This is not it is not trivial at all. Okay, there is a proof in the book, but I want to prove it in a little bit different way. So this is easier for me to understand, and I want to give a special case for you, and I want you to think, because this what I tell you is immediately generalizable to the most general case. But before doing that, I want to. So my claim is that m and k have the same parity. So how we do that? The first thing I want to do is to define you something. Let me give you a polynomial with n variables. Okay? And then I give you alpha in Sn. Okay? I am defining something for you. This is not the proof the book actually is. You can see it. You cannot see it in the book. Usually physicists like this proof more, and I think it's a very beautiful one. Okay, so alpha belongs to Sn. My goal is to define for you what do I mean when I say alpha acts on a polynomial. It becomes a new polynomial so that the indices are changed according to this alpha. In other words, this is my definition. So semicolon equals to P of x. Instead of 1, I write sig alpha 1. And then x, instead of sub 2, I write alpha 2 up to x sub alpha a. Yes? This is what I am defining for you. If I give you a polynomial with n number of variables, and if I give you a bijection from S sub n, what do I mean by alpha acting on the polynomial? I mean this. Okay, so let us see. This is a very simple example. Let me give you a simple example. For example, let us work in S3. Let me change my color. Let us work, for example, in S3. So let us say alpha belongs to S3. And then let me write alpha to be 1, 2, 3, and to be 2, 3, and 1. This is alpha. And let me give you a polynomial with 3 variables, x1, x2, x3, whatever you like, a polynomial. For example, 2x1 minus 3x2 to power 2x3 plus 5x to x3. This is the polynomial, okay? And what do I mean by sigma acting on P? Okay, by sigma acting on P, I mean what? I mean the same P whose indices of the indices of the variables are changed according to this. Sorry, this is not sigma. This is alpha. according to this alpha. It means it is P of X index not 1, index alpha 1. And then the next one X alpha 2, and the next one X alpha 3. So that is the definition I wrote here. So if you have a polynomial and if you have a permutation, what do I mean by applying the permutation on your polynomial? It means rearrange the indices of the variables according to your permutation. So it means that instead of x1, write x alpha 1. Instead of x2, write x alpha 2. And instead of x3, write x alpha 3. Okay, and let us continue. So what is alpha 1? Alpha 1 is 2. So this becomes P acting on x2. Alpha 2 is 3. So it becomes x3. And then x alpha 3 becomes x1. So this means that, this is my definition. When I apply alpha on this polynomial, what I mean the same polynomial in which I have a rearrangement of its variables according to the given alpha. Understandable for everyone? Yes? And if I insist you to continue, can you tell me what do you write? Because P is already given to you, and I want to know what is the answer to this one. So what happens if I continue here? So you see, this x2 is playing the role of x1. So wherever you see x2, you put x1. Wherever you see x2, you put x3. Wherever you see x3, you put x1. That's the meaning. Is that right? So if I want to write it down, it becomes 2. Instead of x1, I write x2. And then you see the coefficients are left intact. x2 is played by x3 now. And x3 to power 2. And then I have x3, which is being played by x1. If I am making mistakes, please let me know. And the next one is plus 5. Okay, I want to wait for you. What should I write here?
x3.
In principle, I should write x2, but x2 is the second location. So it is x3, and then
x1.
x1. So do you understand? So this is a very simple thing. So if I give you a polynomial and I give you a bijection, what do I mean by applying the bijection on the polynomial? Means exactly this. So the coefficients are left intact according to the bijection I give you. You rearrange the variables. Yes, that's the mean. Okay, but now hopefully you agree with me. You need to convince yourself of that as well. If I have two of them, so if I have a polynomial P and I have alpha first and then beta, so if I want to know this, I hope that this is not hard for you. You first apply alpha and you get a new polynomial, and then you apply beta on that and you get a new polynomial. So you do it 2 times. Yes? So what does it mean? It means that I apply alpha first, I get this rearrangement, and then I look what beta is, and I will apply beta on that one again. It is not very hard to see that this relation is correct. Very simple. Any questions? Why is that correct? I mean, if you're suspicious, that's not very hard. You see, if I apply alpha, let me take x1, x2, and x3. What is the meaning of this one? It means P of x alpha 1, x alpha 2, and x alpha 3. That's the meaning of the first one applied. Now beta is going to act on this one. So beta acting on alpha P x1, x2, x3 is equal to beta acting on this expression. P acting on x alpha 1, x alpha 2, and x alpha 3. Yes, and now beta is acting. So beta will act on the indices. So this becomes P of x of beta acting on alpha 1, x of beta acting on alpha 2, and etc. X index beta acting on alpha 3. Yes? But what is beta alpha acting on 1? for example, beta acting on alpha 1 is nothing except beta alpha acting on 1. It's very simple, it's not very hard, you should convince yourself. Okay, but why this is important? Any questions regarding applying a permutation on a polynomial? Just rearranging the indices, that's it. Okay, but now there is a very famous polynomial called van der Monde polynomial. Polynomial. Okay. So, and I don't know, have you heard this before? Probably in linear algebra you might have seen this before, but if you haven't, let me write it. For example, van der Monde polynomial, let me show it with V. Okay, and let me write it only for 3 variables to make it simple. So x1, or let me make it for 4 variables, because these 3 is very simple. 2 and 3 and 4. So I want you to remember, this is a guy, a mathematician, and this is a polynomial called van der Monde polynomial. What is that? You start with x1 and write it minus x2, and then you write x1 minus x3, and then you write x1 minus x4, and finished. And then you start from 2, you write x2 minus x3, and you write x2 minus x4, finished. And then finally you have x3 minus x4. Multiplication between all of them. This is called van der Monde polynomial of 4 variables. Is that clear? Okay, so I want to test your intuition now. Let me ask you, if T is a transposition, so I will emphasize here, T is a transposition. And my question for you is this. What do you think will happen if I apply the transposition on van der Monde polynomial? This is so you need to sit down and convince yourself what I am telling is true. But let us try to discover that. For example, can you give me a transposition from S4, any transposition you like, a cycle of order 2. Okay, so give me any one you like. For example, let us take T to be 2 and 4. Do you agree? This is a transposition, one of the possible transpositions in S4. Now my question is that, can you tell me what happens if I apply this transposition on the van der Monde polynomial? Just wait a little bit, I will ask you. Is the question clear? So we learned how I can apply any permutation on any polynomial. But now I have changed my question to a very particular one. Instead of any bijective, any bijection, any permutation, I have only one single transposition. And instead of having any polynomial, I am focusing on van der Monde polynomial. And my question is that, what do you think will happen? Yes?
Maybe we change x2 to x4 and x4 to x2.
Okay, but that's correct. I will do that. I will change to x sub 2 to x sub 4 everywhere, and x sub 4 to x sub 2 everywhere, but I will not change anything else, because that is only changing 2 and 4. But my question is that, intuitively, what do you think will happen at the end of the day if I do these transpositions? Yes, you raise your hand.
It will be the same polynomial, but I'm not sure if it will change.
No, that's the whole tricky point.
Yeah.
No, it will not go back to the same polynomial. It will go to the same polynomial if this is a symmetric polynomial. It is not symmetric. Okay, so what happens? Let us test. Any other one? So, do you think it will change or not? So what I want to do in this polynomial, as you said, I want to change 1 to 2 to 4, 4 to 2 everywhere. And I want to see what will happen. So let me change my color. But of course, what I am telling you is for this special case. But it is very simple to sit down and convince you what I'm telling for these 4 variables, it will remain the same for any number of variables and any transpositions, not just 2 to 4, 4 to 2. Okay, so let us write this. I want to apply this transposition here. So instead of writing it again there, so let me just change it. x1 will not change. x2 will change or not? Yes, it will be x4. Do you agree? So this becomes this after applying. So let me write t acting on this. Let us see what happens. So what happens here? Nothing. What happens here? This becomes x4. No. This becomes x1, nothing. But this becomes x2. Yes, if I am making a mistake, please shout. Here, what happens? This becomes x4, do you agree? This will not change. This becomes x4. This becomes x2. Here, this becomes the same. This becomes x2. First of all, do you agree with what I have written? I have kept 1 the same. I have kept 3 the same. I have changed 2 to 4 everywhere, 4 to 2. Let us see what happens. So, you see this one is exactly this one. Okay? And then what happens? This one is exactly this one. But look, here I have x2 minus x3, but here I have x3 as minus x2. Yes, do you see? The yellow one is x4 minus x3, but in this brownish one I have x3 x4. So far I have a minus sign difference between them. Yes. So so let me see which ones we checked. x1 minus x4, x1 minus this one we checked, x1 minus x3, x1 minus x3 we checked, x1 minus x2, x1 minus x2, x1 minus x2 we checked. They are the same, nothing has changed. x4 minus x3, x3 minus x4, so one minus sign we checked. x4 minus x2, x2 minus x4. Yes. I am making a mistake because there should be one minus sign coming out. Can you see that? Because this also gives me another minus sign. Yes. So this is not good. x3 minus x2.
That's another minus sign.
Yes, there is another minus sign here. Yes. So how many minus signs I will pick? 3. So it is a little bit, I know, but this is a very, not a subtle thing to sit down. If you do it, you will always pick a minus sign. So what I am claiming, and I was not proving it in general, but the proof in general is very similar to what I am telling you here. My point is that if a transposition, any transposition, acts on Vandermonde polynomial, it gives you minus that. Okay, yes.
Is that because it's only one transportation?
Pardon?
Is that because only one transportation? If we got even number of transportation, would it be even though it would be itself, right?
So I don't know exactly how to answer your question, but you have to think about to make it right. One very simple way, if you knew a little bit linear algebra, it was much simpler. Because there is a theorem in linear algebra that this Vandermonde polynomial can be written as a determinant. Okay? As a determinant of whose first row is this one. And its second row is this one. I'm sorry, this is 1. This is x2. And etc. There is a theorem in linear algebra that if you expand this determinant, which is called the Vandermonde determinant, you will get Vandermonde polynomial. Okay, but now it is very simple if you know that theorem, because when I apply the transposition, what happens? It will interchanges 2 rows. And there is a theorem in linear algebra, if you change the rows in 2 rows in a determinant, the determinant will pick up a minus sign. So if you knew that theorem, it was a piece of cake. You just don't do anything. Because you know that the Vandermonde polynomial is this determinant, and applying a transposition will interchange the corresponding rows. And if you change 2 rows in a determinant, the determinant will pick up a minus sign. But this is also possible. I actually really convinced myself at home that if you work a little bit of indices in a general case, you can come up with this idea that it will pick up a minus sign. Okay, so you can sit down and work it out. This is a very elementary problem. Okay, so I hope that I could convince you that this is the case. Yes? But how do you think this will solve my problem? Do you remember what was my problem? My problem was that if you give me alpha and I manage to write it as m number of transpositions and you manage to write it as k number of transpositions, m and k are simultaneously both even or both odd. How can this help you to understand that? Yes?
No, I mean, it follows from this that if it's an odd length and it doesn't change the sign, and I think you can no, I don't know. I'm not sure how to do it.
That's why I was trying to see if I do a permutation to this polynomial. If it's an even number, in this case it's only one transposition, which is odd, then we get minus.
No, what I'm saying that if you take van der Moon determinant,
Yeah.
van der Moon polynomial,
Yeah.
and you pick one single transposition, and apply that one single transposition on van der Moon, the van der Moon will pick up a minus sign.
Yeah, I mean, if we do it twice, it will come into itself.
Yes?
And to it,
Yes,
all
yeah, exactly.
numbers we got
Exactly.
minus.
Okay, so why? So that's exactly true. So what should I do now? You see, alpha. So what I'm saying is this: I will apply alpha to van der Moon determinant. Sorry, to van der Moon polynomial. Okay, let us calculate this. Okay, so what I do instead of alpha, I use my decomposition. Yes. So what happens? It becomes tau 1, tau 2, up to tau m, acting on van der Moon polynomial. But you use your own decomposition. So you apply alpha, but with your decomposition, tau prime 1, tau prime 2, up to tau prime k, and acting on the van der Moon determinant. Yes? This is my decomposition. This is your decomposition. But now what I am asking you, can you tell me what is the result here? What can I write as a formula here? Yes?
It's -1 to the power of m.
Yes. Van der Moon. Yes, because if, so you see, as exactly as you said, if there are odd number of them, I will end up with a negative sign at the end. If there are even number of them, I will end up with a positive one. Do you agree? Every time that I apply, I pick a minus sign. How many of them are there? M of them. So I will pick m negative signs, which becomes -1 to power m. Is that right? This is the one I calculate. But this is the one you calculate. Can you tell me what will be the answer?
-1.
It's -1 to power k multiplied by the van der Moon determinant. But both of us are calculating the same object. I am calculating alpha 1, alpha v, this is my answer. You are calculating alpha v again, this is your answer. So these two should match. So this means what? It means -1 to power mv should be -1 to power kv. Yes, so this means that this minus sign, -1 to power m, is equal to -1 to power k. So this means that either both of them are simultaneously even or both of them are simultaneously odd. Is that right? The general proof is exactly the same thing. It's not something very strange. Okay? Any questions? Everyone is looking at the watch, I know, okay, but we will stop now. Okay, so we'll have, so you are very conditional. When it goes past the sound, I can feel it in your faces, okay? Anyway, sorry for that. Thank you.